Hi everyone, welcome to the GATE online video lecture. My name is Balasubramanian, working as an associate professor in the Department of Computer Science Engineering since 2008. Have got 22 years of experience. So with my expertise, my today's subject is actually, I'm just going to cover a GATE video lecture on the subject programming and data structures. And programming and data structures, let me tell you something about it. It is an important paper as far as some CSE student is concerned, and more questions will be coming on DS for every GATE exam question paper. And it is not only for GATE students, even if a student has to get placed in a campus interview in a very good company, he should be very strong in GATE data structure syllabus. He must know the nook and corner of data structures. So he should be very good, very strong in the coding part especially. So this paper is going to help you in clearing your campus interview as well as in your GATE examination. Let me give an overview of programming data structure syllabus. So this is what the subject syllabus is. So section 4 is all about programming and data structures, and we have topics like programming in C, particularly recursion, and remaining all topics are coming under data structures: arrays, stack, queue, linked list, trees, binary search tree, binary heap, and graph. So today my topic is actually binary search tree. I would like to give an introduction about binary search tree and would like to solve few problems on that. Yes. Let me tell you the basic concepts of binary search tree. We all know that binary search tree is a type of binary tree in which each node follows the binary search property. Am I right? So the properties are always, we have a root, left child, and right child. As we know the basic concepts, the left child contains only nodes with values less than the parent, and the right child contains nodes with values greater than the parent. That is what the concept of binary search tree, in particularly about left child and right child. So we know that the both left and right subtree have to follow the binary search tree property always. So this is what binary search tree all about. The binary search tree operations are insertion, searching, and deleting. Our main objective is to insert an element, we go for insertion. If you want to search an element in a binary search tree, we go for searching. If you want to delete an element in a binary search tree, we go for deleting. So these are the primary operations of binary search tree. I would like to explain each and every operation in detail, because questions will be asked might be asked on every topic of binary search tree. Am I right? There might be questions on insertion, searching, and deleting also. The thumb rule of insertion, right? If you want to insert an element in a binary search tree, first you have to compare the node element with the root, right? If it is less or smaller, you just go to the left subtree and do the insertion over there. If it is greater than the parent or root, you go and insert the element in the right subtree and repeat this process until the correct position is actually found. So this is what insertion algorithm all about. And searching a node element. For example, I have a binary search tree. It has got a root, left subtree, and right subtree. I just want to search for a particular element, whether the element is found in the binary search tree or not. So first you have to start from the root. Am I right? And if the search element is equal to the root element, the search is found, your job is done. If not, if the search element is less than the root element, you have to search the entire left subtree, right? If the search element is greater than the root, you have to search in the right subtree. Yes, and again in the left subtree you have to follow the similar property, or again in the right subtree we have to follow the similar property. This is what searching all about. Yes. Deletion. We have three cases in deletion. Just imagine I just want to delete a node element which doesn't have any left or right subtree. It is the only element in the tree. So that is, it is the only child, right? So you can directly delete the element. First case. And second case, a node with one child. Yes, if a node with one child, if you delete the root node, then the child becomes the root. Yes, third case, a node with two children. Yes, so in that case you have to replace with in order successor, right? So smallest in the right subtree, or in order predecessor, largest in the left subtree. So this is what the thumb rule of deletion. So the three cases are leaf node, what we have to do it. If a node has one child, what we have to do it. If a node has two children, what we have to do it. So this is what the three operations of binary search tree: insertion, searching, and deletion. Right, most of the applications, there are many real-time applications where we are using these operations extensively. So this is what DS all about. Yes, you'll be having a real-time programs in your campus interview where your real skill is actually tested. So one has to be very strong in the basic concepts of data structure is to clear the programming rounds. Next, a small example of binary search tree. I have taken a small example, right? So 50 is in the root, and you have a left subtree. Yes, we have a, let me take a marker. Yes. Just imagine this is your root. Am I right? This is your root, and this is your left subtree, and this is your right subtree. Am I right? Okay. So you know always the in order we have three types of traversals. I'm just going to cover this in the upcoming topic. So before that, I would like to give a small introduction about in order. In order, yes, elements will be in the node elements should be arranged in the ascending order. That is actually called as in order, right? So 20, 30, 40, 50, 60, 70, 80 is the in order. And I'm going to do a search on 60, whether 60 is available in the binary search tree or not, right? So we know that binary search tree is a type of binary tree which always follows the properties of binary tree. Am I right? So the search element 60 is compared with the root. 60 is actually greater than 50. So you have to do your search in the right subtree. Am I right? Now again 60 is compared with 70, which is less than 70. So you have to come to the leftmost part of your right subtree, which is actually 60. Now 60 is found, so your search is actually done. So this is how you have to search an element in your binary search tree. Am I right? And inserting 65 again. So inserting 65, let me erase it. Right. Yes, I'm just going to insert the element 65. So you always all your operations have to be carried out only in the root first, right? So 65 is compared with 50, which is 65 is actually greater than 50. So you have to go to your right subtree. Again you have to compare 65 with 70. So 65 is actually less than 70. So you have to come here, right? And again 65 have to be compared with 60. Yes, so 65 is actually greater than 60, so you have to insert your element here, right? 65 should go right of 60. So this is how you have to do your insertion. All these are basic operations of binary search tree. Yes, right. And with this, I'm just going to the next topic. Today's topic, binary tree traversals. Yes. Fine. So binary tree traversal, what is binary tree traversal, right? So binary tree traversal in which every node of a binary search tree has to be visited exactly once, right? In a specific order. So this is what the definition of a binary tree traversal. Every node in a binary tree has to be visited exactly once in an order. So what is that order all about? The types of traversals available in data structures are, we know that the two famous traversals are depth first traversal, we call it as DFT, and breadth first traversal, we call it as BFT. Okay, so what is DFT and what is BFT? I would like to give an introduction in the next slides. Fine. So depth first traversal, visit node in a binary search tree as deep as possible before you backtrack it. Okay, so nodes have to be visited as deep as possible. That is what actually called as depth first traversal. Yes, before you do your backtracking. So it is of three types. We know that it is in order traversal, pre-order traversal, and post-order traversal. Am I right? So in order traversal actually left, root, right. Okay, and pre-order traversal is root, left, right, and post-order traversal is left, right, and root. So let me give you how to understand this traversal, right? Let us wait for a moment. Okay, if root comes in the middle, right? If root comes in the middle, we actually call it as in-order traversal. If root comes before, we call it as pre-order traversal. If root comes at the end, you actually call it as post-order traversal. That is what the meaning is, am I right? So post-order, yes, so your key element is root. I'm talking about root. If root occupies the middle position, I call it as in order. If root comes first, we call it as pre-order. If root comes last, we call it as post-order. So we will not forget this anymore, right? So always we'll remember. So in order traversal, root comes in the middle. Pre-order, root comes before. Post-order, root comes at end. So the definition of in order traversal is you visit left subtree first, and you visit root next, and right subtree at last. Pre-order traversal, you visit root first, then you visit left subtree, then you visit your right subtree. Am I right? So post-order is you visit left subtree first, right subtree second, and root at last. So this is what the property of all these traversals. Fine. So with this, I'll move to the next slide. Okay, fine. What is breadth first traversal? Otherwise called as level order traversal. Right here, how we visit the nodes, right? So nodes are visited level by level from top to bottom, left to right. So this is what the property of breadth first traversal. We visit nodes level by level from top to bottom, left to right. We have an example, right? So this is implemented using a queue. Is very much useful in shortest path problems and hierarchical representation in your data structures. So this is what the application of BFT. Next, I have a small example, right? I have a binary search tree. Let me take the marker. Yes, I have a binary search tree. Now you have to tell the in order, pre-order, and post-order for the given binary search tree. Am I right? We know that in order is always left, root, right. Am I right? In order is always left, root, and right. It is right always. Got it? Yes. So as far as this tree is concerned, this is your root, and this is your left subtree, and this is your right subtree. So in order, look at your left subtree first, right? Again in left subtree, you have to look the leftmost element, which is your D, right? So D. So D, so left, root, and right. Okay. So which is D, B, E. So this subtree is traversed. Then you have to go to the top. right? So now you come to the root part. So left is actually over, left is being visited, so you have to write root part, which is A. Then come to the right subtree, you have got again a right child. Yes, so this is your rightmost subtree. You have only two elements, C and F. Apply again in order property, which is left, root and right. There is no left child, we have only root and right, so which is C and B. So this is what your in order all about. Okay, similarly pre-order and post-order. Similarly pre-order and post-order. So what is pre-order property? I'm just coming to the pre-order. So pre-order, root comes first always, right? So pre-order property, root comes first, then left, then right. Am I right? Right. So root. So A is the root element of the given binary search tree. A should be specified. Then followed by left subtree. Again in left subtree you have to apply the property of pre-order, which is root, left, right. So B is the root again, and D and E, left and right. Right, so this is done and this is done. Now you're coming to the right subtree. Again you apply the pre-order property, that is root, left, right. So C occupies the root element. There is no left child for C. You have only right child, which is F. So pre-order is actually over, right? Now I'm just coming to the last type of depth first traversal, which is post-order. Right, so post-order, root occupies the last, root comes at last, right? So which is left, right and root, left, right and root. So coming to the leftmost subtree is, again in left subtree you have to apply this property, left, right and root. So your D is the leftmost element, okay, and E is the right element, and B is the root element. The job is done, right? So this is over. Now again, right, you have to look into your right subtree. Right subtree, again apply the same property post order, which is there is no left child. There is no left child here, and you have right, which is F, and you have your root, which is C, right? And finally you just come to your root element, which is A. So this is what your post order all about. And level order is actually your breadth first travel. Yes, you have to visit the nodes level by level, right? Level 1 A, level 2 level 1 A, level 2 B and C, and level 3 which is D, E and F. Got it? So this is what binary traversal for a small example. So with this I'll take you to the gate question. Okay. Fine. So my today's gate question is, the pre-order traversal of a binary search tree is actually given. Okay, is actually given. Let me take the marker. Yes. Fine. So the pre-order traversal of a given binary search tree is actually given in the question, right? Which one of the following is the post-order traversal of the tree? So you have to find out the post-order traversal of a given binary search tree. Am I right? So we know that the pre-order traversal is actually, what is the property of pre-order? Root comes first. Am I right? So root, left and right. Root, left and right. This is what the property of pre-order. Am I right? And so here, so we know that for the binary search tree, so can you find out the root of the binary search tree from this? So pre-order traversal is actually, traversal is from root, left and right. Am I right? So root comes first. So here, from the given node elements, we can find out the root, right? So 15 is going to be the root of the binary search tree. So 15 is going to be the root of binary search tree, right? Yes. Now, post-order traversal. Talking about post-order traversal, so what is the property of post-order? Root comes at last. Am I right? So left, right, and root. root comes at last. So we identified that 15 is the root of the given binary search tree from pre-order property. Am I right? So in post order, root comes at last. So 15 is the root which comes at last. So in the given two options, we have 15 as the last element in option B and option D. So option A is incorrect, option C is incorrect. Am I right? So root in post order, root comes at last. So 15 is the root element. So option B and option D has got 15 at last. So from these two options, we have to find out the right option, right? Now the next clue is actually, let us write the in-order traversal. We know that in-order traversals, all elements are sequenced in ascending order. That is actually called in-order traversal. For a given binary search, if a tree follows the binary property, right? So in-order traversals always, elements will be sorted in the ascending order. Am I right? So So the in-order traversal is actually, let me write the in-order for the given question. So in-order is, elements should be sequenced in ascending order, right? So which is 10, 11, 12, 15, followed by 16, 18, 19, 20. So this is what your in-order property is, right? So with in-order, I can do the post order. With in-order, I can do the post order. Let us do the post order, right? Fine. So in post order, we know that very well, right? Fine. So let us construct a binary search tree, right? So 15 is going to be the root element, right? So 15 is going to be the root element, is 15, and 10, 11, 12 is less than your, I'm applying the binary search property, okay? I'm just constructing a binary search tree with this, right? So 10, 11, 12 is less than your root, it comes here. So 10, 11, 12 occupies the left subtree, and 16 remaining elements is greater than the root. 19, 20 occupies the right subtree. Am I right? Yes, right subtree. Fine. Again, next, after 15, we have the next element is 10. So 10 is the root. So in 10, 11, 12, again 10 is going to be the root, and 11, 12 comes here. 11, 12 comes here. Again, the next root is actually what? 12, right? So in 11, 12, again 12 is going to be a root, and 11 comes here. Am I right? Yes. Now, okay, so fine. So since I don't have space, let me draw this right very clearly. Let me draw this very clearly. Yes, from the top. From the top, right? So, okay. Yes. So the in order is actually, right? So the in order is actually, element should be sequenced in the ascending order, which is 10, 11, 12, 15, 16, 18, 19, 20, right? We know that 15 is the root of the binary search tree, right? So let us construct a binary search tree with binary tree property. 10, 11, 12 is less than your root. Okay, so with this in order, let me construct a binary search tree, and 16, 18, 19, 20 are greater than the root. It should come in the right child, right? 16, 18, 19 and 20 comes here, right? The next root is actually, after 15, the next root is actually 10. Am I right? So 10 becomes the root, and 11, 12 occupies right. After 10, 12 becomes the root. Am I right? 12 becomes the root here. So 12 is going to be the root. 12 is going to be the root element, and 11 comes here. Am I right? Next, 11 is going to be the root. Fine. After 11, we have 20 as the root. So 20 will be the root, and 16, 19, 18 are less than 20. It occupies left of 20. And after 20, 18 is going to be the root. So 18 is the root element, 16 comes left, and 19 comes right. Am I right? So this is what your binary search tree. Now let me draw you a clear binary search tree from this. Am I right? So 15 is your root element. Got it? And left subtree 10, and you have your 12 here, 11, right? And here 20 is the root of the right subtree, followed by 18 less than 20, and 16 less than 18, and 19 greater than 18. So this is what the complete binary search tree all about. Now the post order traversal, we know very well that the post order is root comes at last, okay? So which is left, right and root, left, right and root. Let us apply this property, okay? So I'm going to have a traversal from the root. So post order, I have to look into the leftmost element. So leftmost element of this binary search tree is actually 11. Got it? So almost we have got the answer 11. Let me check the answer once again. We have got the answer B, because in B and D the first element, in D the first element is 19, which is wrong, and B has got the first element is 11. So B is going to be the right answer. You can just conclude it. But let me explain the concepts fully, right? So 11 and look into the right. So this particular subtree doesn't have right element, right? So 11, your right element is null, and again you go to the root element 12, right? So 11, 12, fine. Again coming back to 10, so you're in this main root. So again here left, right, root. So left is actually your 10. Again you have to traverse to the right subtree. In right subtree again you have to apply the same property, and is coming to the rightmost subtree here is the rightmost subtree has got the elements 16, 18, 19. Apply the post order left, right and root, okay? So which is 16, 19, 18. 16, 19, 18. Again you come to the rightmost element, which is 20. Again you come back to the root element, which is 15. Okay, so this is what the post order traversal all about. So similarly you might any questions can be asked in binary search tree traversal. So with this concept you must be able to solve any problem on binary search tree. Okay, so I've covered you the basic concepts of binary search tree, its operations, and binary search traversals, and there and two types of traversal, with this depth first traversal and breadth first traversals. All these traversals are hugely applied in all applications of real-time applications. Am I right? Yes. So this is what my today's class is all about, and my next class on data structures will be covered on the topic heap. Right? I'll be taking you heap. I'll cover you the basic concepts of heap, and would like to solve some problems on heap. Yes. So thank you. See you in another great video class once again. Yes. Thank you.